In this lab activity, we will find a numerical aperture, and then finding the numerical aperture, we will find the acceptance angle of the optical fiber, because we know that optical fiber is very thin fiber that we use, and there must be an acceptance angle, because it is the maximum angle that you can give to the optical fiber to transmit from one end to the other end, and beyond that angle, if you incident that light, it will not transmit to the other end. Okay, so there must be some acceptance angle that each optical fiber has. So using this experiment, we find what acceptance angle that you can give to a particular optical fiber. So this is your experiment that we will perform today, and these are the practice required to perform this experiment. We will need an emitter, because that emits the laser light, and we are also using fiber stand here to that place where we are placing our optical fiber on this fiber stand, and we need a concentrator that we optical fiber we are using, detector, because the other end of the optical fiber we are getting the light. So how we are finding that that light is there, and how much intensity is there, so we are using detector over there, and that is a photo detector, because when light comes, it gives you the output, and it is giving you the output in terms of the current. So we need a detector and output unit to get that light at the output. So these are the pretest required for performing the experiment. Yes, and we are also using laser, and we know what is laser, and it's light amplification by stimulated emission of radiation. And in this way, we are getting monochromatic light and high intensity light we are getting using this laser. So optical fiber is basically a technology that associated with the transmission of light pulses from one end to the other end, and it could be shorter distances, or it could be larger distances, or the longer distances. We can classify optical fiber in two types when we are classifying in terms of the material. Okay, because we can use a glass material, and we can also use the plastic material for the transmission of light. So depending upon the material you are using for the transmission, it could be glass or the plastic. So there are two types of the optical fiber, and in this optical fiber, you can see here, this is a core material where this transmission of the light takes place, because light enters in this core material, and we are covering this core material with the cladding. So and this optical fiber and how transmission is being takes place, that is totally based on the total internal reflection, and this cladding has a less refractive index as compared to core, so light has to travel from denser to rarer medium. So when it reaches at the surface of to media, so total internal reflection takes place when this angle is greater than the critical angle. And this material we are using maybe of the glass or the plastic. So when you are using we can use glass and the plastic. So and these material are very thin, and these are delicate, because it's very thickness is very small. So these are very delicate. So to avoid any kind of damage, we are covering these material with some material that has more strength as compared to cladding and the core material. So that material we also name as buffer, because in optical cable we have bundles of optical fibers. So even these optical fibers have they are in bundles, so we need to protect them, and to avoid the damage, we are covering these material with a buffer, and then we are also using jacket over there too, because if we want to transmit the light from one end to other end, and if you want to transmit your data from for the longer distance, if you maybe in the kilometers distance, so these must be protected, and so those materials are being used to cover that. So these buffers and the jackets we use to protect and to avoid the damage of the optical fibers. So these are the optical fibers that we are using in this experiment. And here we are also using a screw gauge. You know that when you use a simple scale, and its least count is 0.1 centimeter. So even when you use 1A caliper over there, so its least count is 0.01 centimeter. So when you use a less least count instrument, so obviously your accuracy of the value is very large. So to get precise value and accurate value, we use an instrument which has less least count. So even this screw gauge has less least count than the 1A caliper also, and its least count is 0.001 centimeter, or you can say it's 0.01 millimeter. So we are using screw gauge to vary the distance of that detector, and that affects the light outcome we are getting from the output unit. So in this screw gauge we have two scales, one main scale and other is the circular scale. So we are moving this screw gauge in that way that its circular scale will move, and how much its circular scale will move according to that main scale reading you are also getting using this screw gauge, and you know how to use this screw gauge. This is the output unit that we are using to get the current in form of the digital form. Okay, so this gives the current of that detector. And now this is the theory behind the optical fiber, and I have told to you that what mechanism behind this optical fiber is. It's totally internally reflected. Light is totally internally reflected and guided in this core material, and we are finding the numerical aperture of this optical fiber. So what is this numerical aperture? So we know that if you have a core material, if it is in the cylindrical form, and if light is coming from this area of cross section, so when you are using a screen over there, so you will get a light on this screen. Okay, so when you are getting this light on the screen, it will give you a circle over that screen. Okay, so similar diffraction pattern you have also find, but this is not the diffraction. But in that experiment, you find out that there are some different circles you are getting on the screen, for the maximas and the minimas. But in this case, we are using an optical fiber, and light is coming from this end of the optical fiber. So you will get a circle. You will get a circle on the screen. So when you move this screen, obviously your this radius of this circle will change, and we are finding this numerical aperture, what this ability of this optical fiber to collect and confine, how much light it can collect. This is the numerical aperture of that optical fiber, and because what angle you can give to this optical fiber, so that you can find out the light at the other end. These numerical aperture and the acceptance angle, they are related to each other, and this is the acceptance angle, that is the maximum angle that you can give to the optical fiber, so that light can enter and it can be emitted from the other end of the optical fiber. So we are finding this numerical aperture and acceptance angle of the optical fiber in this experiment, and these are related using this formula. You can see this numerical aperture, we abbreviated this as NA. This is the numerical aperture, and it is equal to sine theta A, where theta A is the acceptance angle, and sometimes in this expression can also witness sine theta maximum, because this acceptance angle is a maximum angle that you can give to an optical fiber, so that light can be entered and it can be emitted from the other end of the optical fiber. So this numerical aperture, that is equal to sine theta A, and it's also related to the refractive index of the two material, that is core material and cladding. And always we know that core material has high refractive index as compared to cladding. So because light has to travel from denser to rarer medium, so core has high refractive index, and this formula we can evaluate from the Snell's law. Okay, so we use that Snell's law, that sin I by sin R. So depending, we are getting this expression for the numerical aperture of the optical fiber. So we are using this formula to calculate. So this is the experiment, and this is simulation link where we are using this experiment, numerical aperture of the optical fiber, and you can see operators are there to perform this experiment. But before that, we have to place these operators on this breadboard, and for that, firstly we need a emitter that emits a laser light. We need this concentrator, this fiber stand, and this is the detector we are using, and this is the output unit, and this is the optical fiber that we place between this concentrator and this fiber stand. This is the arrangement to perform the experiment. So when you have placed all these operators on the breadboard, you will click on the start button. So when you clicked on the start button, you can see first picture show you the arrangement that you have made for this experiment, and then is the screw gauge that we are using, and this screw gauge we have attached with the detector, and this when light comes on this detector, it is giving the current in this output unit. So when you have made this arrangement, and then we will click on switch on button. On this switch on button means that you are giving power supply to this emitter, and it will emit the light. So you have given the power supply to this emitter, and it is emitting light. So we are getting this light that pass through this optical fiber, and it is reaching to the detector. So you will see when you click on the switch on button, you are getting your light in the detector also, and it has passed through the optical fiber. So we can see here from the output unit, it is giving you 0 0. So we need to move this detector so that we get some current, because light is on this detector but it is not giving the current. So we have to adjust these distances in a way that you get the current in this output unit. So in this experiment, you have also option to select the fiber. So it is giving you glass fiber or the plastic glass fiber. So when you use this glass fiber, and you have also option to select the color of that laser. It could be red, green, and blue. So if suppose I have selected red laser light, and then you have this option to for the detector distance. So in this experiment, this distance you will keep it fixed firstly. So if suppose you have taken 2 millimeter detector distance, and using this screw gauge we are varying this distance x. So if suppose you have using this slider, you have varied this, you can see your screw gauge is moving. Can you see this on the screw gauge? Because when we are moving, you see your circular scale is moving. So you have to increase this detector distance x with the 0.5 millimeter. If suppose you see when it is at the minimum value, and you see your zero of this circular scale is coinciding with the main scale of this screw gauge. So move in a way that you will get. Suppose then again 0 come, so one rotation has been completed. That means it has moved 0.5 millimeter. Okay, so then again move with the, when again 0 comes, so it means it has again moved 0.5 millimeter. So in this way you will move your this circular scale to have 0.5 millimeter step size, and you will see when you are increasing this by 0.5 millimeter. So you see still it is not showing any current in this output unit. So now you can see it's showing the current. So in this way you have to move this screw gauge, and you are getting the current in the output unit. So that is clicked on this show vernier reading. Actually this is showing you the screw gauge reading. So when you click on this show graph, so you will see you will have a graph over there, and in this experiment you have to plot this graph, and you see when you are increasing your detector distance, now you can see your current has been increasing. After certain distance, it is again started decreasing. So in this experiment, what you will do, you have to adjust the detector distance in a way to get this current in the Gaussian form. Your current is coming because after certain distance of the detector, its current also decreasing. So you have to adjust your detector so in such a way that your intensity or the current you are getting maximum. So when you get this graph, so you can see you have to find out this I maximum. So what is this I maximum now? It's 0.369. So when you get this I maximum, you have to take 1 by E of this maximum value. So when you take this 1 by E of the maximum value, that means you are dividing this I maximum by 2.71. So if suppose it is 0.369 and divide by 2.71, if suppose you are getting some reading. So it's around 1 point something, point 1. So it's you have a two values of that x, because you see you have a maximum value at one distance, it's around 9 millimeter, but when you take 1 by e of that value, so you are getting two values of x, because along this I maximum you have on this left side of this I maximum, and again you same value you will get on the other side or the right side of this I maximum. So two value of x you will get for same value of I by e. You have to find out firstly I maximum, then find out I by e of that maximum value. So you will get the two values of x. So what two values of x you are getting? So when you are taking the difference of those two values, you will get the value of r of that circle that is being made on the screen. So light is entering from the one end and it is emitting from the other side of the optical fiber. And when you are not using that detector over there, but you are using a screen, so when you are using a screen, you are getting this circle on the screen, and when you move this screen, so you will get different circle over there, okay, different radius of the circle you will get, and you have to adjust in a way that your intensity of that circle should be maximum. So you can see when you are varying your distance x, so this you are varying from the screw gauge, and z distance you have placed firstly, and then using the screw gauge you are changing the x distance. So when you are changing your distance x, so you are getting this graph and you are finding having this I maximum firstly, then after finding this I maximum you are finding this I by E, and it's I maximum by 2.71. So you will have two values of this I by E. So what the two values of that x make a perpendicular over there. When you take the difference of these two values, you will get the 2r. The 2r is the this is the diameter of this circle where you are getting the maximum intensity. Okay, so you can find out this 2r from that.